Airfoils at ultra low Reynolds numbers, like at 14,000, are really interesting. In fact, Reynolds numbers that low are interesting in general. And that is because when you're that low, the viscous forces are relatively high. And so all the typical flow features that we know, like vortices, are really difficult to have because the viscosity just tears them apart. And in terms of an airfoil, things get even more interesting because now the flow near the surface is so slow that it doesn't really have much energy to stay attached, even under slightly adverse conditions. In this podcast, we'll be looking at how extreme surface roughness at low Reynolds numbers affects an airfoil's performance. So even with regular roughness, we won't necessarily do too much because the viscous forces just take all the energy away that the turbulence creates. But if we have macroscopic roughness, does that do very much? So the roughness we're talking about is literally just crinkling a wing like you see here in figure 1. So let me scroll up to figure 1 here and zoom out. And for those of you who are just listening to this podcast, you can watch it on Spotify and or YouTube. And on YouTube, we also have other goodies as well. So in figure 1 here, this crinkling effect is just pretty much extreme surface roughness. We have these macroscopic bumps. This idea actually comes from Dragonflies, which we use this design to help prevent laminar separation bubbles by introducing more turbulence into the flow. So if you don't know what laminar separation bubbles are, check out the podcast in the link in the description. We've gone through them quite a few times and in different ways to look at their applications and just what they are fundamentally. So to look at this phenomenon of these crinkle cuts like this very macroscopic roughness at low Reynolds numbers for airfoils, we're looking at this paper called Aerodynamics Study of the Corrugated Airfoil at ultra low Reynolds numbers. So for these crinkle cuts, we mentioned that they come from dragonflies. They're inspired from dragonflies. And dragonflies actually have this airfoil profile. And the thing with dragonflies is that they fly up to a Reynolds number of about 50,000. But in this study, the authors are looking at a Reynolds number of about only 1,400 and lower, actually 200 as well. So a Reynolds number of 200 is really low. And at this Reynolds number, the flow physics of a lot of different objects changes dramatically. So while in nature we can conclude without doing too much testing that this extreme roughness or this crinkle cut is probably going to be effective, otherwise evolution wouldn't let it happen, we can't really conclude that this easily for this such a low Reynolds number and for just a typical airfoil flapping regularly. What's more, these authors are also interesting, as I mentioned, in determining whether this crinkle cut helps an airfoil produce more lift and or thrust when flapping, because with dragonflies, that's how they fly. They flap their wings, and that's why we have this crinkle cut. So the reason why this flapping is important is because flapping is inherently unsteady, and unsteady flows are much more likely to produce turbulent structures such as vortices and weird breakdowns of wakes compared to steady flows. So this is particularly true at low Reynolds numbers as well. Now, many researchers have wanted to make their conclusions applicable to insects, in this particular case, dragonflies. So they study airfoils flapping and they go, okay, well, this is how insects must fly. But unfortunately, most, if not all, research on flying insects is incredibly flawed. So for example, only 5 years ago, it was common practice to assume that wings of insects were rigid and didn't bend during the flapping motion. Fast forward a few years, we now know that this simply isn't true. In fact, it's very common for insects' wings to bend during the flapping motion, and even more strangely, this bending affects the dynamic flow physics. For example, how leading edge vortices peel off and where they go from there and how they interact with the wings. The bending dramatically affects this. So where the bending occurs and how much the wings bend all affect the dynamics as well. We still don't really know exactly how much each insect's wings bend, and even between, like, you might have two insects of the exact same species and they may bend slightly differently. We don't really know. This is still just one major unknown. So it's one limitation in insect aerodynamic research. Another one is the frequency of flapping and even the path the wings take during the flight and how this path might change with changing frequency. All of these limitations, and I'm sure that there are many more that we haven't covered or even considered, make research on flying insects quite uncertain. So this paper looks at dragonfly wings, but we're not going to be looking at it from that angle. We're going to be looking at it more from just macroscopic surface roughness such as this on a generic wing flapping. And that's because of these major limitations to this insect research. So I should stress that the results from this flapping motion are not necessarily applicable to all flapping motions, but just for this exact flapping motion covered in this paper, which we'll go through in a little bit. So they also did a very interesting thing in this paper. they obviously looked at this airfoil with the crinkle cut, which you can see here in figure 1a, but they also looked at an airfoil with the exact same resulting thickness and camber, but without the crinkles, which is shown in figure 1b. So they pretty much just got this airfoil, which is crinkled, and then they just did a geometry going all the way over this line covering it, and that's now the airfoil. And this is a clever idea because by doing this, they remove the effects of the camber and the thickness from the equation and can focus on the crinkle cut itself, because effectively figure 1a and figure 1b have airfoils with the exact same maximum thickness and camber effectively, but one has a pretty much a smooth surface, the other one has this jagged surface. So that's effectively that macroscopic surface roughness. So the authors also looked at a simple flat plate without the crinkle cut. So to research the effects of this crinkle cut, they used CFD, and in particular Fluent. They used URANS, I should mention, from what I can tell, because it's unsteady, and they also solved this in 2 dimensions. So let me go down to this CFD part. Now, one important thing to note is that the authors assumed that because the Reynolds numbers were low, there was no turbulence. So they didn't solve any turbulence equations. They assumed purely laminar flow. This is generally a good assumption to make. Is this generally a good assumption to make? Well, if you don't have the resources to spend, then you can make that trade-off, as we'll go into in a second. If you do have the resources to spend, then this assumption is probably not a good one to make. But the authors likely made this assumption to speed up the solving time. So given that trade-off, assuming that the flow was laminar is fairly acceptable considering how low the Reynolds numbers were. I would have liked to have seen what the effects of the crinkles had from a turbulence point of view, but we won't know from this study. So let's move on to the wing flapping, because there is one parameter in particular that is quite important when it comes to flapping. And this is a parameter called the reduced frequency, which they have specified just here in this equation 6. So the reduced frequency is the ratio of the flapping speed to the free stream velocity. So with the flapping speed as a numerator. In addition to this parameter, the authors also mentioned the airfoil's propulsive efficiency and the thrust. Neither of these 2 parameters are unusual, as expected, we also have the lift coefficient, which we'll know and love. So let's move on to the CFD setup. We're just looking at the CFD here now. So the computational domain looks fine. The wing has quite a lot of area and not too close to the walls. You can see it can flap quite nicely. One thing that I thought was what would happen if you flap the wing at different angles. So if you were to have the wing straight here and then you flap it, that's different to if you have the wing at a 45-degree angle and then you flap it with the exact same motion. How that affects the aerodynamics, I'm not too sure, and that's very complicated, which we're not going to go into this paper, but it just came as an idea to me, what would happen then. So if you had an airfoil at different angles of attack flapping, you'd want to have a curved inlet. The reason for that is what I've gone into in other podcasts, but in a nutshell, it means you don't have to remesh the domain every single time you change the angle of attack. You just change the inlet flow angle and you're fine. Whereas with these authors, they had the wing constantly at 0-degree angle of attack and then they moved it dynamically with the same effective 0-degree angle of attack throughout the entire phase. So the straight inlet is fine. So the authors did a pretty cool thing, one thing we don't really see too much. So to see if the domain size was fine, the authors did some CFD runs for different domain sizes. This is very uncommon, but a great idea. So in this figure here, we see that they had the domain at different sizes. And this is because you can see if the domain that you have is big enough or not. One way that a lot of people do CFD is that they just specify the domain and they either just use a good judgment or tables that they know from other research to specify the domain size. But these researchers actually looked into the domain size, so that's quite good. So the potential problem with a too small domain size is that the flow cannot evolve as it should. You will constrict it so that vortices become squashed together and interact far more, and in ways that they shouldn't. The weight gets squished as well, and the flow over the object gets pushed onto the object more, which can reduce its tendency to separate. These are just a few major ways that a too small domain can severely affect the flow, and hence the forces. So in figure 4, we see the results of these different domain sizes. The authors went from a domain where the inlet was only 5 chords from the airfoil, and the airfoil was 12 chords from the airfoil downstream, all the way to when the inlet was 12 chords from the inlet and 24 chords from the outlet. Unfortunately, they didn't look at the sides and top and bottom distances, but this is definitely better than nothing, looking at the inlet and outlet distances. So this distance here from the inlet to the leading edge and the trailing edge to the outlet, that's pretty good just to see. So the results show that at different distances, the lift and drag coefficients throughout the flapping cycle were almost identical. So the smallest domain of the inlet 5 cores upstream and the outlet 12 cores downstream was sufficient. Changing it to a much bigger domain had almost no effect to the lift coefficient and a slightly more greater effect to the drag coefficient, but still not very much, like maybe 5%. As for the mesh generation, the authors looked at a mesh independent study as well, where the mesh ranged from a coarse level of 680,000 cells to the finest mesh of 1.1 million cells. And we have the results here in figure 6. So all the mesh levels pretty much gave almost exactly the same lift and drag coefficients throughout the flapping motion. So that's really good. I mean, you can see they just like fall on each other almost perfectly. There's only maybe a couple % difference, which we can't even see with these lines. Maybe down here, there's a little bit of a change, and maybe here. So overall, they're very good. Now, the authors said that when they zoom in, they found some differences up to 5%. So they went to the medium mesh, where they found a smaller error between the medium and fine compared to the coarse and medium. So they concluded that the medium mesh is fine. And this is the right way of doing it, where you have 3 different courses to the mesh, and you pick the medium one where it's very similar to the fine mesh. For example, if you had, in other podcasts, we had the authors doing 3 meshes, and when they found that the coarse mesh was exactly the same as the medium and the fine, the results. Now, that's not a great independent study, because what that means is, okay, you get a mesh which is good, but you may be using more computational resources than you need to get that independence. Alternatively, if you had a mesh independent study where the coarse dramatically changed from the medium and the medium dramatically changed from the fine, and then you just said, okay, we'll use a fine mesh, that's also not good either, because, okay, you're using less resources of your resources, but you're not getting potentially an accurate result. Here, the authors did it well, where they had 3 different mesh coarsenesses, that's a hard word to say, and they found that the medium mesh was much more similar to the fine mesh, so the grid was starting to converge, the results. So they picked the medium mesh over the coarse mesh or the fine mesh. So that's fine. And in addition, they also looked at the time step study, which is, again, what you should be doing when you have an unsteady CFD setup, and it's something that a lot of researchers don't do, but these authors did really well. So because it's an unsteady simulation, there's a time step aspect for each iteration. So the simulation is marched forward 1 time step each time you iterate forward. And if you march forward too much, so you, like, let's say each time step you go forward by 0.1 seconds, you miss out too much of the transient flow physics, and too much of that can change the solution. If the time step is even larger, then the simulation will simply diverge and it'll crash, so it won't solve. On the other hand, if you go to a very small time step, so like 0.00001 seconds, then for some simulations that's good, but for other simulations that's overkill, and you're just going to be using far more resources than you need. So the authors looked at time steps ranging from 100 microseconds to 10 microseconds, the latter being the better choice, because it's they found here in figure 7 that the grid converged the time step study converged quite nicely, with the lift coefficient being very similar between the finest time step and the second finest time step. So I must say I'm very impressed so far with these authors' CFD setup and validation process. They looked at the time step, the mesh independent study, and the domain size even. That's very thorough. So they have done very well so far. And let's look at finally the experimental validation data, which we see in figure 8 here. We have the lift and drag coefficients of the flapping airfoil compared to the experimental data, which are in these non-solid lines, or I should say not the black line. The black line is the CFD. The data closely follows the same trends as the experimental data. There are some differences in the magnitudes though. So the author suggests that these differences are due to the fact that the experimental data were 3D and not 2D, which is what the CFD is. So overall, the CFD is looking good, I think, because that would definitely explain why we get some changes in the magnitudes. And even still, between the different published data, there is some differences between their results. So their CFD lies in the middle of all these ones, so I think it's quite good still. So let's move on to the results. In figure 9, we can see that the crinkled airfoil, while stationary at 0 degrees, 5 degrees, 10 degrees, 15 degrees, at a Reynolds number of 14,000, we see these streamlines. At low Reynolds numbers, small vortices form in each of these trough values you can see here. This is for 0 degree angle attack as well. But as the airfoil's angle attack increases, the vortices grow to the point where they almost take up the entire suction side. So when we're at 15 degrees here, you can see there are 2 vortices on the top, and they pretty much take up the entire surface. Now, looking at the lift and drag coefficients in figure 11, we can see that the streamlines, the streamlines that we see here, I would have thought that that would affect the lift coefficient slightly differently to how they did. So if we look at the blue line, which is the lift and drag coefficients of the crinkled airfoil, compared to the red line, which is just the regular flat plate, the crinkled airfoil is producing less lift for this high angle attack. And that's surprising. And the reason why I say that is surprising is because I thought that there might be a chance that these vortices that take up almost the entire suction side, just here, might have acted like artificial thickness and camber for this airfoil. So this is not uncommon to happen. It happens for lamp separation bubbles, where you have these flows on top of the surface effectively isolated from the rest of the flow on top. So the flow that comes over on top effectively just continues on its merry way, and the airfoil is effectively this geometry plus this dead region of flow. Now, it becomes doubly interesting when you consider that these vortices are also low pressure zones, which given their location should result in a lower pressure on the suction side and hence more lift as well. But we don't see that in these figures here. So the fact that we see a lower lift coefficient for the crinkled airfoil is surprising. Perhaps the vortices don't stand on the suction surface indefinitely, but migrate downstream, so there isn't always these vortices present right here. I don't know, maybe that's one reason why we get such a low lift coefficient compared to the flat plate. Interestingly, the flat plate yielded the highest lift coefficient out of all the geometries tested, even the airfoil that was developed, taking the crinkled cut airfoil and enclosing it with the airfoil profile for adequate size. I am very surprised that the flat plate didn't experience flow separation even at 5 degrees. So I think that these results need a little more investigation, because the flat plate is very flat, it's very blunt, and these types of geometries typically separate quite easily, like even at a few degree angle attack, we should be seeing quite a lot of separation, but we don't. So I think that potentially there's some error maybe here for the CFD when these geometries aren't flapping. This is just a stationary airfoil. As for the drag coefficient, the flat plate also has the highest values, which we can see here in the same figure, in figure 11a. Now, this is a little surprising again, because I can't believe that it got such a high lift coefficient, which indicates flow attachment, but a higher drag coefficient than the crinkled airfoil. The crinkled airfoil should have a much higher pressure drag, which would have made this drag coefficient much higher. The authors say that at this low Reynolds number, the skin friction drag is the main component of drag, which I definitely get if the flow is largely attached. But I don't expect the flow to be attached over the flat plate or even completely over the crinkled airfoil. So I expect that the pressure drag should be important here, and as a result, either the flat plate should exhibit a lower lift coefficient and a higher drag coefficient, or a higher lift coefficient and a lower drag coefficient if the flow is attached. So I don't really know what is going on with these results. It may just be that the Reynolds number is so low that some kind of funky flow physics is happening, something that doesn't really make sense at normal Reynolds number ranges. However, to counter that theory, in figure 10, which is the exact same airfoils but at a Reynolds number of 200 instead of 1400, the flat plate and the profiled airfoil and even the crinkled airfoil all have very similar lift and drag coefficients. So if it was a Reynolds number effect where you have a very low Reynolds number, I would expect that would carry through to these figures as well. So I don't really know what's happening here with these lift and drag coefficients and why they're behaving like this. They don't really make sense at the moment. I think additional studies are needed for these geometries. Anyway, in figure 13, we see the static pressure coefficients distributions over the airfoils at an angle of attack of 0 degrees and a Reynolds number of 1400. It's really cool because we can see the peaks from the crinkles all the way down the airfoil. So we can conclude that from these results that the crinkles aren't beneficial for the flat plate's aerodynamics if the plate is stationary. However, let's look at the flapping phase now. So in figure 15, we see the static pressure contours of the airfoil and of the crinkled airfoil on the left, and just the simple flat plate on the right. So let me zoom in a little bit so we can see them a bit better as we go through. That's probably a little bit too much. There we go. Okay. So both of these crinkled airfoils and flat plates are flapping with the exact same motion. Interestingly, there isn't much of a difference between the two in terms of the static pressure distributions. The contours look very similar with only minor differences seen. For example, in figure 15D, so these two here, at the trailing edge of the crinkled airfoil, just here, the pressure isn't as low as for the flat plate, just here, but both still have a low pressure zone. In this figure, another difference occurs in this region, and that is for the crinkled airfoil, only one low pressure zone can be seen in this region, whereas for the flat plate, there are two distinct low pressure zones, here and here. You might be able to argue that the low pressure zone on the crinkled airfoil sort of got sucked into the other low pressure zone, but we don't know that for sure. But even still, they are a little bit different, and these are kind of the only differences that we see in these contours. Apart from that, all plots look almost identical. So that means that this extreme surface roughness, so this crinkled like macroscopic roughness, didn't really change the flow physics too much, at least at this ultra low Reynolds number. They didn't really compartmentalize the vortices or alter the breakdowns very much. So something that we see is when we have like quite jagged surfaces, sometimes the vortices can get caught in these surfaces, and then that changes the flow physics. That didn't happen here for this flapping airfoil. The authors also put the lift and thrust coefficients next to each plot. So let me scroll over a little bit. These plots here. So we have the lift in the blue and the thrust coefficient in the dashed red as we go through the flapping motion. 0 is when we start to flap, and 1 is when we've completed the entire flapping motion. As we go through, they've just highlighted with these dots where we are compared to the contours, what the contours, these pressure plots correspond to with these figures. So these two airfoils mimic each other quite closely in terms of the lift and thrust coefficients. For example, throughout this entire flapping process, the crinkled airfoil produces a maximum lift coefficient of about 3.5, which we can see just here. And the same flat plate, without the crinkles, produced a lift coefficient of maybe 3.6, just marginally higher. The thrust coefficients appear to be identical as well, with the maxima pretty much the same, hovering at just below 2. So we can see here it's from about 2 to about 0, whereas here it's about 1.9 to about 0. They're very similar. And that's the thing with flapping flow physics and resulting forces. They're so sensitive to the frequency of the flapping and even how the wings flap and how much they bend and the motion that they take, that these minor changes to the geometries can dramatically affect the forces. For example, in figure 17, which is down here, we have the effect of changing the flapping frequency on the lift coefficient of the crinkled airfoil. So at 25 Hertz, which is the blue line, the lift coefficient is between -1 here and +1, depending on where you are in the flapping. But not even doubling the flapping frequency to 40 Hertz, which is the red line here, results in a lift coefficient 3 times as large, between -3 and +3. Then, increasing the flapping frequency even more to 60 Hertz results in the lift coefficient jumping even more to 9 and -9. So when you look at the relationship between the flapping frequency and the resulting lift coefficient, you can see that it's highly non-linear. Increasing the flapping frequency by 140% resulted in an 800% increase in the lift coefficient. This non-linearity is also shown in figure 18, where the reduced frequency is plotted against the lift coefficient, just here. Now, one thing to note is that I think that these lift coefficient values are averaged over the entire cycle. I'm not 100% sure because the authors don't seem to indicate that these lift coefficients values correspond to this or to the maximum or anything, but I'm pretty sure that's what they mean by here. So these values are the maximum lift coefficient seen throughout the flapping cycle compared to the reduced frequency and the thrust coefficients as well. Anyway, we can see that increasing the reduced frequency non-linearly increase the lift coefficient. What's more, as the reduced frequency increases, the wing's efficiency drops from about 65% all the way to 37%. It almost halves. So from this study, we might be tempted to conclude that a crinkled airfoil, like a dragonfly's wing, doesn't do too much for the lift or the lift coefficient, or the thrust coefficient, sorry. But that's the thing. This was found for just one particular type of flapping. There are so many ways that you can alter how something flaps, from the frequency to the path the wings take, to how the wings flex, to even if the wings move through the cycle with a constant speed. Perhaps they slow down at certain points to reap greater benefits, or speed up to jettison certain flow features away. We don't really know, and it changes between insects and even between dragonflies, I would assume. Or I would even imagine, because that's how evolution works. We have minor differences between things and they get magnified through generations. So the fact that dragonflies do have them, these crinkles, and they don't seem to use the crinkles for anything other than flying, indicates that they are beneficial for flight. Otherwise, they wouldn't have evolved to have them. But for this study, we can conclude that the crinkles and the associated extreme surface roughness didn't do too much. Perhaps the Reynolds number needs to be higher to like a dragonfly's Reynolds number range, I don't know. Or maybe the flapping motion needs to be different. It's hard to tell right now. So that brings us to the end of this podcast, amigos. If you really like this, I really like this podcast actually, because it's very complicated with a lot to keep track of, and that's the thing with flapping motion, that there is a lot to think about. So I really like this podcast, and if you liked it too, make sure to give it a like. It helps us out. And if you want to see more like this, click the subscribe button or the follow button, whichever platform you're on. And if you want to get better at CFD or aerodynamic theory, like we've gone through in this podcast, check out our courses in link in the description. And if you want to make your experiments 2 to 4% more accurate, get yourself an atmosphere hawk. It's an instrument we make to make your results more accurate, because it measures the density of air. The reason why this is important is because the density of air changes from day to day, and even from hour to hour and minute to minute. For example, you come into your wind tunnel in the morning, then you come back after lunch, and the density of air has changed by a few percent in just a few hours. The density of air is affected by the temperature, barometric pressure, and humidity. So having even you in the wind tunnel changes the density of air, because you're pumping out heat, you're pumping out water from your breath, and you're talking. What's more, the density of air changes even more than 2 to 4% between days, months, weeks, and seasons. 10 to 15% changes are very normal, which means that you need to take them into account in your experiments. What's more, if you don't take them into account, then your CFD inherits that error as well, because you're using your CFD at a certain density. Your experiments are taken at a different density, and that's not going to line up. And that's the thing. A lot of people, they look at their CFD and they go, okay, it doesn't line up with the experiments. That means that CFD is wrong. That's not necessarily the case. Maybe your CFD is exactly right and your experiments are exactly right as well. It's just they're not comparing the same thing because they have different densities. The atmosphere hawk is really that error for you. So get one for yourself, and you can find it in the link in the description. And with that, I'll see you in the next podcast. Peace out, amigos.